Okay, so we are going to now take a look at solutions of acids and bases that have a common ion. And so, say we make a solution of, I don't know why my example here doesn't match. Make a solution of HF and its sodium salt of the conjugate NaF. Okay. We typically say sodium salt because all salts with sodium are soluble. So if we put these two species in solution, NaF completely dissociates to sodium ion and fluoride ion. HF is a weak acid. It's got equilibrium with H plus and F minus. So both of these form F minus. So both of these equations have F minus as a product. That's the common ion. Okay? An ion that's found in the equilibrium of the weak acid and that forms from the salt. It's common to both equations. So if we add F minus, more F minus to this equilibrium, okay, thinking back to chapter 15, which way does the equilibrium shift to gain equilibrium? Reactant side or product side? Yeah, the equilibrium is going to shift towards the reactant side. Okay, so if we add more F minus, the equilibrium shifts to HF, the reactant side. And what happens to the pH? It increases. So we have less H plus, pH increases, becomes more basic. Okay. All right, so that's sort of the idea of what's happening with buffers. We're adding, in a buffer, we're going to add a weak acid and the salt of its conjugate base, or we're going to have a base and a weak acid, no, a weak base and the salt of its conjugate acid. So what a buffer does, and you've probably seen this maybe in your bio classes or somewhere else previously, a buffer resists change in pH when small amounts of acid or base, strong acid or base, are added. Or when we dilute the solution, or when the temperature is changed. Okay? So it buffers a change in pH. It basically makes it so it doesn't occur to a large extent. So we're going to think about an acid adding a weak acid and the salt of its conjugate base to a solution, and we're going to have two equilibria in the solution at play at one time. So let's say we add a general acid, HA, and the sodium salt of that conjugate base, NaA. Okay, so that's just sodium acetate or sodium citrate, whatever it may be. Okay. So the first equilibrium is going to be the weak acid plus water forming the conjugate base and acid H3O plus. And we also have A minus plus H2O in equilibrium with HA and OH minus in solution. So both of those are happening simultaneously. Okay. For example, we have our HF. Forms F minus. If we add sodium fluoride, that F minus is going to react with water to form HF and OH minus. All right. But what happens if we add a strong acid to the buffer? So we'll take our HF and NaF buffer. Okay, we've got HF and F minus. Again, our sodium fluoride is completely dissociated, right? That's our salt. We put that in solution, and now we have this F minus plus H2O equilibrium. All right? So what happens if we add HCl to the solution? As we know, HCl completely dissociates to form H plus or H3O plus. So we're adding acid to the solution. What does it react with? And your options are either HF or F minus. F minus. Okay. Can't react with HF. That's an acid as well. So it's going to react with the conjugate base. And so we're going to have H plus. Let's do H3O plus. I think that'll look nicer right here. H3O plus plus F minus reacting to form HF plus H2O. Okay. So when we add strong acid to a buffer, it's going to react with the conjugate base. We form HF, right? And we know that has the equilibrium. And we'll reform some F minus. So this is how buffering works. It's sort of cyclical. So if we have our H plus, H3O plus, it reacts with F minus to form HF. But HF has that equilibrium to regenerate some of that F minus. And so that's why the pH changes very little. Okay, so both of these equilibria are occurring simultaneously. What if we add a strong base? What's it going to react with? HF or F minus? It's going to react with HF. It's going to react with the acid to form water and F minus. And again, that F minus is going to have an equilibrium and regenerate some HF. Again, why the pH changes very little. Now eventually you can break down a buffer, you add enough acid or strong base, and you completely deplete any of the weak acid or weak base reserves. If we look at this graphically, this is for acetic acid acetate buffer. So here's a buffer with equal concentrations of conjugate base in the sort of blue color and acid in the pink color. If we add strong acid to that solution, it reacts with the weak base, forms more acetic acid. If we add hydroxide, it reacts with the acid to form more conjugate base, acetate ion. Okay? Again, the pH changes just a little. The dotted line is showing our initial concentrations. Okay. So if we look at this graphically, here we have a plot of pH on the y-axis, moles of acid added in one direction on x, and moles of base added in the other direction on x. Have you guys done a titration yet? Plotted a titration? No.
I think we did, but not for acids.
Not for acids.
Was it? No.
Citric acid? You didn't plot it? Okay. For a weak acid titration, there's a region of the titration curve that looks like this. It's called the buffer region, and that's what this is trying to show. Okay, different thing. So what this is trying to show is that this is our perfect buffer. We haven't added any strong acid or strong base to it. So 0 moles of H3O plus or OH minus added. As we add a small amount of strong acid, the pH starts to decrease, and eventually it'll decrease sharply, become much more acidic. That's where we end up with breaking down our buffer. Same thing with adding hydroxide. Okay? Add a small amount of hydroxide, the pH increases just gently until eventually we've depleted all of that acid that it can react with. If we look at what a titration curve or a curve might look like, not a titration curve, for a strong acid, or for adding a strong acid or base to water. Let's draw this. Here's moles of H3O plus increasing towards the left, moles of OH minus increasing towards the right, and we have pH. We'll say we start around here for our pH. We'll say it's 7 because we're in water, and it's nice water solution. As soon as we add acid, the pH decreases. And eventually it's not going to decrease much. Or as soon as we add base, the pH increases. Okay. It's going to look more like this, as opposed to the gradual curve of a buffer. It's going to be much more sharp and look something like that, like a giraffe. Anyone else see that? He gets eat a leaf. That's, yeah, you have to draw a giraffe, be able to draw a giraffe for the exam. Giraffe is for a buffer. And the second one, the one that looks like now a giraffe, is for pure water. So we're looking at how the pH doesn't change very much in a buffer versus how it changes drastically in water. A giraffe. Oh, there's a question. Yes, good. We're going to bring us back on topic. Hang on, everyone. I can't hear the question. Yeah. The first graph. Yeah. So that's the first. So this ties into the concept of buffer capacity. Okay. Just a couple more minutes. So buffer capacity is the ability of a buffer to not let the pH change very drastically. And it is a measure of the amount of acid or base that can be added before a significant change in pH occurs. What does significant change mean? It means going from pH 4 to pH 2, okay? Something like that. And really the way we calculate this, I don't need my leaf color anymore. Is the change in pH in the denominator. I don't think this is in your textbook. And then the, I think this is moles of either OH minus or H3O plus. But basically it's just how much acid or base is needed to change the pH by some amount. The buffer capacity is dependent on the ratio of weak acid to conjugate base or conjugate base to weak acid. Usually a 1-to-1 ratio is of weak acid to conjugate base is the best. That kind of buffer resists change in pH in both directions, either acidic or basic, better than something that has the ratios off a little bit. But even a ratio of 1 to 10 or 10 to 1 makes an okay buffer. The other thing is that the pKa for the acid of the buffer needs to be close to the desired pH. So if you want to make a buffer at pH 4, I think, I'm trying to recall off the top of my head, I think acetic acid has a pKa around 4.6. So you can make a acetic acid buffer and it would resist pH change around pH 4. Here's a question to think about. If more base is present in solution than the acid, is the buffer more resistant to the addition of acid or base? More resistant to the addition of acid, right? Because there's more base to react with. And the opposite is true. If there's more acid present in solution, it's more resistant to change in base. Okay. All right. We are going to next talk about calculating the pH of a buffer. I know we only have a few minutes left, so I'm going to set this up for you. Let's say we take 100 mils of 1 mole per liter acetic acid and 100 mils of 2 mole per liter sodium acetate. And we want to find the pH, and we're given the Ka for acetic acid. The only equilibrium that we need to worry about, only one equation, is that with acetic acid on the reactant side and acetate on the product side. Okay? Now you can solve this problem just like we've done with every other weak acid, weak base problem, except now you have an initial concentration of both acetic acid and acetate ion. So there's going to be something here and something here, but not here. The reason I didn't just plop in our concentrations is because we have to mix these two things together, okay? Once you have that, you can set up an ice table, determine the concentrations of acetic acid and acetate after they mix, and solve. Or you can use what we call the Henderson-Hasselblock Equation, where we calculate the concentration of conjugate base, A minus, base, and acid, and we use our initial concentrations as if they were equilibrium concentrations. This equation, if you only remember one thing from today, this equation only works for buffers. Okay, you can't use it on salts. You can't use it on weak acids. You can't use it on weak bases. All right? When we meet again on Wednesday, we will talk about actually calculating pHs of buffers. Until then, have a great afternoon. It's beautiful outside.